Hi, everyone. Good morning, good afternoon, good evening, depending on where you are. Welcome to FusionEPtalks. This is a student-led webinar on fusion science and technology. I'm Oak. I'll be your host today. I'm delighted to introduce Nick McGreivy, who is going to be our speaker. Nick is a fourth-year PhD student with broad research interests across computational physics, machine learning, nuclear energy, and policy. In practice, this means maybe he isn't super an expert in anything exactly except automatic differentiation, which is the subject of today's talk, but has broad interests and is working to expand and connect multiple different scientific endeavors. He is hoping soon to begin his thesis work on data-driven computational physics at Princeton. Nick is from Washington, D.C., but he currently lives in Honolulu, Hawaii, where he's been finding time to go surfing every day amidst a big selection of research. Without further delay, I will mute myself and hand it over to Nick. So welcome and enjoy the talk. Nick, you're good to go.
Great, thanks, Oak. Yeah, so this is research I've been doing. Well, it's actually not my research. This talk is a tutorial, and the goal is for all of you really to understand automatic differentiation. And so if you have questions in particular during part 2 of this talk, I really want you to understand those things in particular. And so yes, I've been doing some research in the 3rd year of my PhD and now 4th year. But I won't be talking about that research just because it's not needed for you to understand AD. Cool. So this talk is in three parts. Part 1, I'll be talking about how AD is practical for computational science and computational physics, and in particular for optimization. In part 2, I'll talk about how automatic differentiation is elegant, both in theory and in practice, and then in part 3, I'll be talking about how automatic differentiation is powerful or can be powerful, and this is kind of still work in progress that the AD community is working on, for linking automatic differentiation and computational science and time-dependent nonlinear simulations. Great. So how is AD practical for computational physicists? So first, let's understand what it is. And this is a definition we'll understand better throughout the course of the talk. But the definition that I give is that AD is a technology for automatically computing the exact numerical derivatives of any differentiable function represented by a computer program, including arbitrarily complex simulations. And so to compute automatic derivatives of a function, you program that function using an AD software tool. So this is being able to get derivatives of computer programs is very useful, and it's had a lot of different applications. So some of them, the most prominent probably is machine learning, and you've seen things like TensorFlow and PyTorch. You've probably heard those names before, even if you're not an expert in machine learning. And what those are at their core, they're automatic differentiation libraries, and then you've kind of wrapped them with this package to make it easier to use for machine learning. But then things like learning protein structure, the protein folding problem that DeepMind made major progress on this summer, was really driven largely by automatic differentiation as well as some machine learning. But then things like solving quantum mechanics problems, solving the Schrodinger equation as an optimization problem for many bodies, this has been very successful as well. My research in stellar coil design, differentiable ray tracing, optimization of fluid simulations, etc. So these all come from Gies's tweet. Gies works at CERN. If you're curious to see a whole bunch of applications that people have put out, you can go to his tweet and read the comments. And then this is an exchange that I liked as well. So Sam says we've done some crazy things with AutoDiff over the years, and then Gert mentions how neural networks were kind of a Trojan horse for getting AutoDiff into physics. Now it's worth mentioning the history here, which is that AutoDiff has been around for a long time. It was really worked on mostly in the 80s, 90s, early 2000s, but by some folks in Germany, and they really developed the theory, and they really laid the groundwork for kind of the later interest in machine learning that was popularized, interest in automatic differentiation that was popularized through the machine learning community. So there's been a lot of niche applications of AD that's been around for a while, but kind of the best software tools that are around were developed through machine learning, and so this has made AD a lot easier and kind of as Gert says, it's been a Trojan horse for getting AD in a lot of different areas. And then there's one example which I'll show you here. See if I can get it to load, which Sam did. So what he did was pretty cool, actually. So he started with this block, which was representing a wing and a wind tunnel. And then he ran this time-dependent nonlinear simulation of the fluid equations around that wing. I'm sorry, that's the wrong one. Here it is. And so he had this time-dependent simulation, and he took the final state of the simulation, and he turned that into an objective function which maximized lift and minimized drag. And then he took this square block and he optimized it using gradient descent to find the best wing shape that perform that objective function. And so he was able to differentiate through this nonlinear time-dependent simulation. And this isn't always easy to do, but it's something that I think and Stefan here thinks is a big part of the future of automatic differentiation. And so I'll be talking about that at the end of the talk, how AD interfaces with kind of more traditional computational physics. One more example that I'll give is this is a stellar quote design code, and it's not the one I use in my research. It's kind of the bare bones, simplest thing that I could come up with. And it's not 25 lines of code, but it would be if you cut out all the comments and imports. So this is a quote design code, and we don't need to understand the details to understand why automatic differentiation is really nice here. So there's a couple things that we need to understand. So the first thing we need to understand is this line right here, import jax.numpy. And jax is an AD library. And we're able to import jax's version of numpy, which to us as a user looks and feels like numerical Python, right? But in practice, there's a whole bunch of things going on behind the scenes that are really, make this a desirable library. And then what I do is I compute some mathematical functions. In this case, I compute some objective function related to the coils in the magnetic field. And then what I do, and here's kind of where the automatic differentiation magic happens, is I take that function and I use this function transformation grad, which is part of the JAX package. And so I take my objective function and it gives me a new function, which gives me the gradient. And so then I can use that function to perform gradient descent. So why am I showing you this? Why is automatic differentiation, awesome for stellar flow design? Well, it's awesome for a couple reasons. One, being that A, it's very efficient. B, the code is very simple to write. But that's not really what's awesome. What's awesome is that is this thing grad, and this thing grad does two things for us. Number one, it allows us to not have to write by hand, which in practice would be pretty difficult, doable, but annoying and time consuming, and error prone. Write out by hand the derivative functions corresponding to each of these functions. And so that saves you as a programmer a lot of time, and it makes things a lot easier. The second thing that it does is it really allows you to change this objective function quite easily and not have to recompute the derivatives, which means that in practice, it's very easy to iterate on different objective functions, different regularizations, different models, basically. And so as someone who's doing optimization, and optimization isn't always easy, right, to get the right objective function. And if you're someone who wants to iterate on your objective function, which a lot of people do, then then having AD really makes that a lot simpler and easier. Cool. So this is part one of the talk. Now, in part two of the talk, I'll get into how AD is elegant, both in theory and in practice. And hopefully, this is the part that I kind of want you guys to understand. So feel free to ask questions. And so we'll see how AD is elegant in theory in the sense that it's based fundamentally on the chain rule, and how this allows us to compute the derivatives of arbitrary functions using known building blocks. And then we'll see how in practice the AD software packages have made performing automatic differentiation really effortless and simple. And I should have cut out this line. Now, for the next couple slides, I'll skip kind of ideas like reverse mode and forward mode, which are really important aspects of AD theory and someone understanding it, but I'll talk about those later in the talk. Okay, so what is really the essence of automatic differentiation? The essence of automatic differentiation is the chain rule, or the multivariate chain rule. And so suppose I have a function which is made up of what are called primitive functions, u and v, in a composition. Now, physicists don't often think about composition, but computer scientists do. And believe me when I say that compositions to a theoretical computer scientist is fully general. If you add some bells and whistles, basically, compositionality of functions allows you to express any function, right? So this is a really general idea. And the derivative of that composition is the product of the elementary Jacobians of each individual function, and these Jacobians are matrices. So what is automatic differentiation? Well, automatic differentiation is taking known primitive functions and then, like u and v, composing them together and then computing the derivatives using the chain rule. And for each primitive function, the elementary Jacobian matrix is known by the AD tool. And so what it knows how to do is to take those known Jacobians and staple them together to compute the full Jacobian matrix. So this is kind of the essence of automatic differentiation. How does this work in practice? So here's a very, very simple kind of pseudocode example of an automatic differentiation library and how it works. So what you would do is you would define a class of primitive functions, and this could be addition, multiplication, division, sine, cosine, but then you could have other things. You could define like Fourier transform, for example, as a primitive. You could define linear solve, whatever. And so you define these primitives, and then for each primitive, you define how the function evaluates, and then you also define the derivative of that function, or the Jacobian of that function. And so what your AD library does then is it allows you to compute the Jacobian of any function which is built out of those fundamental building blocks, those primitive building blocks. So here's an example. F1 is just A of B of C, or sorry, C of B of A. But then F2 is something arbitrarily complicated and long, and AD can compute that derivative. So this is kind of the essence of how an AD library works. Now, in practice, AD is very elegant as well. And so there are software tools that have made computing the gradients of functions very, very simple for the user perspective. So this is my favorite library, and a lot of people like this one, and this is called JAX. And JAX basically feels like numerical Python, in that this is some arbitrary function. They just chose tanh, right? And they wrote tanh using what feels like NumPy. And then we've seen this before. They took the grad of that, and they get this grad function, and then that gives them the gradient. So this is kind of the simplest possible example, and it's really, really easy just to take gradients of functions. And so there's been really great software tools. Okay, so there's a lot happening on this slide, and it's an important slide. So let's try to understand it. So suppose and so now I'm going to talk about differentiating function compositions. I'm going to talk about Jacobian matrices. I'm going to talk about forward mode and reverse mode. And so we're going to want to understand how these matrices, what these matrices look like, and how they multiply each other to compute a Jacobian. So we'll do that. We'll do that with an example. So let's suppose I have a function f, which goes from n inputs to 1 output. So this is a scalar function. And what does this remind us of? This reminds us of optimization, right? So in optimization, you have a scalar objective function. And in that function, you perform a composition of primitive operations A, B, C, and D. And so you start with this vector x, right? And so we're performing A, and then B, and then for C, and then output. And for those who just joined, this is a composition of primitives. So the question becomes, how do you compute the derivative of this function? Well, like we said, the derivative of f is given by the multiplication of the primitive or the elementary Jacobian matrices of each. And so since A is going to be going from, Rn to Ra, you have this square matrix. And then, this rectangular matrix. And then you have a series of rectangular matrices. And at the end, because we have a scalar function, then our last elementary Jacobian is 1 by RC. And so if you multiply these together, then you get the Jacobian, right? So notice, and I'm going to have a trivia question for the audience in a second. Notice that, although they may be muted, so this may be difficult. Notice that you can multiply these Jacobian matrices in any order, right? You can multiply from left to right, or you can multiply from right to left, or you can multiply, from the middle first and then going outside. So my question for the audience, and I don't know if this is possible because of muting, what is the most computationally efficient way to multiply these matrices? How do I take these 4 matrices? How do I multiply them in the most computationally efficient way? No matter how I multiply them, right, they'll give me this. But it turns out that the order matters. Does anyone want to try to answer that?
Feel free to raise your hand.
I asked this to the, I gave this talk last week to the PPL grad students, or some of them, and it was a harder question than the professors recognized as a harder question. Jacob, you want to try?
Hey, so do you can you hear me all right?
Yep.
Do you multiply by the 2 left ones first? Because if you do it on the left, then what you get out is a 1 by something matrix, or sorry, 1 by something vector, and that way you keep smaller total matrix dimensions when you're doing this multiply.
Exactly. So you multiply this vector times a matrix, and you get a vector. And then you can keep multiplying from left to right. So you get a vector times a matrix, and you get another vector, and then you can keep multiplying from left to right. And so if I multiply from left to right, like Jacob said, I do 3 matrix vector products, and matrix vector products are faster than matrix products. But if I multiply from right to left, then I do a matrix times a matrix, and I get another matrix, and a matrix product is slow. And then I get matrix times another matrix, and so I've just done 2 matrix products and 1 matrix vector product to compute this Jacobian. So the order really matters when you're multiplying, when you're taking derivatives, and when you're multiplying elementary Jacobian matrices. And so in general, if you have a function f from Rn to Rm that takes time O of t to compute, then multiplying from right to left takes time O of nt, and multiplying from left to right takes time O of mt. And just as a preview, some of you may have heard of something called the adjoint method, right? So I always personally find the adjoint method really confusing. We'll talk about it a little bit at the end of the talk, hopefully. But the adjoint method really is basically just, if you have a function, it's multiplying, instead of multiplying from right to left, it's multiplying from left to right. So that's what the adjoint method is. It's starting with a vector and then multiplying it from the end to the beginning of the function, and then keeping vectors as you go. And we'll see a little bit more of that. Whoops. Oh well, wants me to write. Cool. So before we get into forward mode and reverse mode, there's 2 other things we have to understand. So one is the Jacobian vector product, and the other is the vector Jacobian product. So what is a Jacobian vector product? So a Jacobian vector product, if I have the Jacobian and I feed a vector, which is the column of the identity matrix, then I'm going to get 1 column of the Jacobian matrix. And so that looks like this. And for a scalar function, if I take 1 column of the Jacobian of a scalar function, I just get a scalar. And so if I want to get the full Jacobian, or the gradient of a scalar function, Jacobian vector product is not the way to go. The way to go is going to be a vector Jacobian product. And so the vector Jacobian product you multiply on the left. And this gives you 1 row of the Jacobian matrix transposed. And so the product of the Jacobian here is this row transposed. And then for a scalar function like an optimization, this VJP gives you the gradient, which is the Jacobian transposed. So VJPs are really nice for computing functions from Rn to R. Okay, so this is also an important slide. So what is forward mode and what is reverse mode? So forward mode automatic differentiation is computing Jacobian vector products by taking, this thing here was these four matrices were are the underlying Jacobians that we need to multiply. And we start by tacking on this vector at the end, at the beginning, I'm sorry, and then computing Jacobian vector products all the way down. So vector matrix product, get a vector, vector matrix, get a vector, etc. And in reverse mode, we start with a vector at the end of the function. In this case, it's just it's just the element 1 put in a matrix. And then you multiply from end to beginning, doing, in this case, vector, vector, and then vector matrix, vector matrix, vector matrix from left to right. So forward mode in practice is going to be this Jacobian times this column vector. So that's what you're going to end up outputting. And it's going to be efficient. It's going to be a series of matrix vector products, but for this function f, it only gives us a scalar, which is just one element of the Jacobian. If we feed in, or it really gives us a product, a dot product, right, between the Jacobian and this vector. In reverse mode, or in the adjoint method, these are kind of the same thing, from a certain sense. In reverse mode, you're feeding in this vector at the end, and then you're going to be getting the full Jacobian. And again, you're doing matrix vector products. Any questions on this slide? Because it's kind of an important one. Is it clear? Okay, cool. So here's a summary of AD, just to really make sure you guys understand. So and then we'll get into how automatic differentiation is powerful right after this. So if I have some function which takes an input and gives me an output, and that function is composed of primitive operations implemented by my AD tool, whose elementary partial Jacobians are known, elementary Jacobian matrices are known, then automatic differentiation computes the numerical value of the derivative at the input. And in forward mode, I can compute the full Jacobian in time O of n by performing forward mode n different times to get each of the n scalars in the Jacobian, each of the n columns of the Jacobian. And in reverse mode, I can compute the Jacobian in time O of m by performing it m times to get each row of the Jacobian. Here's some fine print. Just if you have these questions, they're kind of helpful. What makes it automatic? What makes it automatic is that your AD library A knows the partial derivative of each primitive in the library, and B, it knows how to chain those partial derivatives together, either through forward mode or reverse mode. And if you want the full Jacobian, not a Jacobian product, then AD tools can do this, but it's kind of outside the scope of the talk. There's this thing called the JAX AutoDiff cookbook, which is really helpful for understanding a lot of these things. And it's worth spending some time with this if you're going to be using AD. And then there's a connection to differential geometry if you're interested. Great. So I've kind of touched on these a little bit. But from a user perspective, why is AD really useful? If I'm doing research with gradients, research with optimization, why is AD useful? So there's really here's my favorite 3 reasons. So 1 is it's very simple. 2 is it makes gradient-based optimization it is very convenient for gradient-based optimization, and part of this is because your gradients are effortless. And so if I want to prototype new ideas, try new objective functions, regularizations, whatever, then I can just compute a different function, and then the gradient's given automatically, and the optimization is performed automatically. Excellent. So in this last part of the talk, what do I have? About 15 minutes or so before I open up to questions. I'll be talking about how automatic differentiation is powerful. And my goal is for you kind of to see where AD research is headed or might be headed, I hope is headed, and see kind of how automatic differentiation might be useful in kind of not just computing these chain matrix products like we have in in machine learning or in stellar core design, but kind of more useful across the broader range of computational science. And all the theory for this has been developed, I should say, by those Germans I was talking about. The kind of the tools that implement these things are what are being developed right now. And so here I'm going to commit a tragic sin, and I'm going to tell you that all of computational physics can be reduced to one slide. It's obviously not true, but for the purposes of illustration, let's pretend it's true. So you have linear equations, you have time-dependent linear equations, you have nonlinear equations, and you have time-dependent nonlinear equations. And the details of this aren't so important if you're not familiar, but what is important for our purposes is this thing right here, or this thing, however you want to put it. So let's do this thing here. So any of these, this is basically some nonlinear equation, and you can write any nonlinear equation as a vector g, and you say that this equation is a function of some inputs, and it outputs your solution. So this is an implicit equation. And you can set g equal to 0. And then you can solve that using Newton's method or whatever, or something else. But what this means is that if we want to connect automatic differentiation to computational science, then what we need to be able to do is to differentiate through implicit nonlinear equations that can be written as g equals 0, and that take some vector of inputs and output solution u. So you know, and if we wanted to differentiate through nonlinear equations, we would have to do something very similar. If we wanted to differentiate through a simulation, whatever. And so if you're interested, you know, just thinking about maybe optimization of, say, you know, some partial set of partial differential equations, if you want to differentiate through that simulation, you'll need to be able to perform something like this efficiently. So how do you do that? Well, you do that actually with the adjoint method. And so this is also from Gies's tweet that I referenced earlier. And Kyle's a physicist, and Stefan has his PhD in physics but works at Google. And Kyle referenced the adjoint method. And then Stefan says, and this is interesting and insightful, he says, the sad fact is that most or many existing adjoint codes were written by hand rather than the aid of AutoDiff. And so, you know, he's somebody who's been working on these packages, and says certainly this is the way of the future. So this is my hope as well, and this is things that people are working on, and the folks over at JAX have told me this is a goal of theirs as well, is to really make these tools something that you might want to use in broader computational science to perform optimization, to perform differentiation. And there's been some exciting applications of this, in particular the past couple of years or past year. So I have about 10 minutes. Let's talk about the adjoint method. And these equations, I always find very mysterious and confusing. And so if you don't understand it, if it goes over your head, you know, it took me like 10 times staring at these to understand them. And so I'll show you these equations, and then I'll show you how these equations can be more simply understood using the framework of automatic differentiation, where you think of this implicit equation as a primitive function in an AD library, and that really makes, I think, this whole adjoint method kind of stuff simpler. The formulation of the problem is as follows: you have some design parameters, and those design parameters P, you want to minimize them to or change the parameters to minimize some objective function. And that objective function is going to be the solution of some implicit nonlinear equation, like in computational physics. And it's also going to be a function of the parameters themselves. And so the question is, well, if I want to differentiate this, if I want to optimize this using gradient-based optimization, how do I compute the gradient? Well, you can start performing the chain rule and seeing what you come up with. So if we take dfdp, we get a partial, plus we get, you know, this is just the chain rule, right? But we can also differentiate G. And so if we differentiate G, which is always going to be 0, then the derivative with respect to P also has to be 0. And then the derivative is given by the chain rule. So we have this equation and we have that equation. And notice that there's du dp here and there's du dp here. So we can take du dp, we can write it in terms of an inverse matrix, and then we can take that information, that inverse matrix, and plug it in. And so we get this equation here. And this was all going over my head when I first saw it. So if it's going over your head, that's okay. And then you can take this and notice that this is like a vector times a matrix, right? So this is a vector Jacobian product, basically. And so you can write this as a matrix itself. And then you can write the derivative as a partial plus the adjoint vector, which is what this is called, this vector times the times a Jacobian. And the adjoint vector is given by the solution to this equation here. So okay, that's a mouthful. That's a lot of math. It's a lot of calculus. What is really going on here? So and when I understood this, it made a lot more sense to me. So what you can think of this as is as a series of primitive operations that start with a vector P. You perform a primitive operation, and then you get a vector G, which is this implicit equation. And then the process of solving that equation you can think of as a primitive. And that gives you your solution U. And then that solution U, you perform a series of primitive operations to compute your objective function. And then you differentiate that whole thing by going backwards through your, starting at the end of your function and working your way towards the beginning. And so you're passing these vectors along, which are vector Jacobian products. And so df/du is a vector Jacobian product. Lambda is the adjoint vector is a vector Jacobian product. And then this thing, lambda transpose ddgp, is also a vector Jacobian product. And so the full derivative is kind of understood using automatic differentiation technology terminology in this way. And so I write this here. So the constraint equation is a primitive operation. df/du is the cotangent vector, or the vector in the VJP. And so is lambda. Lambda is the solution of the VJP. And then this is what's called the adjoint equation, which is the equation that gives you your VJP. Cool. So I claim that this is a simpler way of understanding the adjoint method. Now, here, understanding this, there's something in the chat. Understanding this is, no, I don't, is kind of important for thinking about how automatic differentiation interfaces with computational science more broadly. And so let's go back to this tweet from Stefan. And Stefan says the sad fact is that most existing adjoint codes are written by hand rather than native autodiff. So how would I in practice actually bring this technique of the adjoint method, which is very powerful, and interface it with this technique of automatic differentiation, which is also very powerful? And the way you do this is using the ability of automatic differentiation to implement custom user-defined primitive operations. And so here is some pseudocode, and this is very similar to the pseudocode of PyTorch, but JAX has similar things that you can do. And so in PyTorch, what you do is you define your forward method, which takes some input and computes the output of that function. So that would be like that. In this case, it would be like taking U and P and performing this implicit solve to give you the solution U, which is the output of the implicit operation. And then you have to implement this backwards function, which you start with the vector in the VJP. And then you would perform the adjoint method analytically in this custom function, and then output the adjoint vector, which is the solution of your VJP. So you would perform the adjoint method potentially by hand, right? But then once you've performed it by hand, you can treat this as a building block as a primitive function in automatic differentiation, and then you can differentiate, you can add it as a smaller part of a larger computation, and then it becomes you get all the benefits of automatic differentiation while taking this custom difficult to differentiate kind of aspect, which is your implicit solve, and differentiate through it transparently like you would any other function in automatic differentiation. So the bottom line, if any of this went over your head, is that automatic differentiation can perform the adjoint method using custom primitive functions, and this allows AD to be used in computational physics. I'll say that the software for doing this, for general purpose scientific computing right now has not been fully developed, and the folks at Google, I think, are working on this. At least they told me they are. And then there's if you're doing finite element method, there's a really good existing software package that I can point you to, but that's less plasma physics and more kind of engineering. I have about 1 or 2 minutes before it's been 40 minutes. So why would you not compute automatic derivatives with AD? So there's a couple reasons. So one is if you have a massive legacy code which you can't rewrite, it's just too complicated. And hopefully in that case you don't have too many parameters, and you might be able to perform finite difference despite the noise. You might be able to perform finite difference if you have enough compute power. If you've already written your code and it already computes analytic derivatives of the adjoint method, you don't need to change it, but next time you might benefit from using AD. And then not all highly specialized numerical routines are implemented by an AD tool, but as we've seen, you can always implement a custom primitive if you really need it. And then the memory cost of reverse mode can be large. I don't get into this, but there's something called checkpointing that helps reduce the memory cost, and it can be very effective for time-dependent simulations. It really kind of getting rid of the memory issues with AD. And then there's this quote by Uwe, which I like. He says, "The automatic generation of optimal adjoint versions of large-scale simulation code is one of the great open challenges in the field of high-performance scientific computing." So with that, I'll say that that's the end of my talk, and you can read more about the adjoint method in AD on this tweet, which I think I've pinned to my screen. So with that, I'll take questions.
Awesome. Thanks so much, Nick. This is really cool. Just to get things started, I guess I had a question while people are thinking. So you mentioned you don't want to use this if you have like a large legacy code already going, because it's just like way too much work to rewrite stuff. So is this something that you have to implement like basically from the ground up when you're writing like a new software, or could you is there a stage at which you could like easily rewrite something that exists before it becomes like way too much work to rewrite it? I don't know what your thoughts are on that.
There are people who have written and are writing software that tries to take an existing code like in C++ or Fortran and differentiate it, take that existing code and automatically differentiate it. I found those to be quite hard to use. I found it's easier just to, in practice, to rewrite something yourself. Yeah. So that is really can be quite tricky to take an existing code. But hopefully you understand how it works, and so you can just do it yourself. Sure. Jim asked to unmute. Oh shoot. Let me start with Jim.
Yeah, Nick, thank you for the talk. I was wondering if you can compute the second derivative with JAX. I mean, not automatic differentiation. I mean, the adjoint method, it's not really possible to compute the second derivative with it, at least to my knowledge. But maybe JAX has another powerful tool. Is it possible?
Yes. So yes and no. So this is a good question. And there's a lot of kind of research on computing high order derivatives, even arbitrarily high order derivatives. So automatic differentiation in forward mode does not have memory issues. and it uses basically zero memory overhead. And so automatic differentiation in forward mode can compute arbitrarily high derivatives. Automatic differentiation in, and you know, as you get to like, you know, an nth order derivative, it becomes, you know, it goes like n squared or something the computational time. So, you know, you might not want to take, or maybe exponential, I can't remember. So you might not want to take like a 25th order derivative, right? But second order derivatives are quite interesting. So if you were to try to take my, you know, if you were to try to compute the Hessian matrix, well, a Hessian matrix is, you know, of a of an n-dimensional function is n by n. And so it turns out that that Hessian matrix is going to use n times more memory than a normal reverse mode differentiation function, you know, compute will. So Hessian can use a lot of memory. And if you have like a 10-dimensional function, 10 parameters, then computing the Hessian can be not so bad. And for example, if I had like, you know, a blockwise Hessian matrix, and I had, you know, if I was doing coil optimization like you and I do, Jim, and I only wanted the Hessian with respect to a particular coil, then getting that particular Hessian might not be so bad, but getting the full, you know, 100 parameter Hessian might be hard. There's another thing which is really interesting, which is this Hessian vector product idea. So it turns out that you can actually get Hessian vector products in sort of the same memory and runtime overhead as normal reverse mode automatic differentiation. And so, you know, sometimes you do need the full Hessian, but oftentimes getting you know, a vector product with the Hessian is good enough, or performing a series of vector products and getting an estimate of the Hessian can be helpful. So, so there's a couple of different possibilities available, and it just depends on what you're trying to use it for. Thanks. And we can talk more about this. Sean Ren, I hope I don't butcher the pronunciation.
Yeah. Yes, thank you. Just have two questions. Does this automatic derivative works with any functions, or it works only with elementary function or combination of elementary functions? Or how is that?
So how does it work with, the question is, how does automatic differentiation work with any function, or
does it work with any arbitrary function?
Yeah, okay. So you know, you can be very mathematically precise, and you can be you can wave your hands. And so I'm going to wave my hands. Well, I'm gonna both wave my hands and then show you what's really going on under the hood. Okay. So you know, any oh god, I don't want to. I hope there's no mathematicians in the audience, because they'll be mad at me. Any function can be differentiated. So what does Stefan say? He says.
Okay. Sorry for the interrupt. I asked this because once I had some problem that is not quite holomorphic. So does that will work the automatic method?
Okay. So so the true answer to your question is that, and this is really what's going on under the hood, is when I define a primitive operation, I define a forwards and I define a backwards. So I could actually, you know, I could define the wrong derivative, right? And then it would compute this chained matrix products of incorrect derivatives, right? And obviously that's silly, no one would do that, because why would you want the wrong derivative? But this is a practical issue. For example, when you have discontinuous functions, right? If you have like the ReLU function, and they do this in machine learning, they say, well, at x equals 0, what is the derivative at x equals 0? Mathematically, it's undefined, but computationally, we need to put a value on it. So there are cases where the derivative mathematically does not exist. And so of course, in that case, you cannot compute it. But what I could say is I could just say, well, for this ReLU function, which has a discontinuity, I could define the derivative at the discontinuity to be whatever I want it to be. And then I could say it's 0, let's say. And so then if I compute the derivative at that discontinuity where the derivative is mathematically not well defined, because I defined it to be 0 at the discontinuity, then computationally it is well defined. So Does that answer your question?
Yes, more or less, but I had some special case in my mind, like it's if the function is not quite holomorphic, you approach
Like a complex function.
yeah.
Yeah, I'm not so familiar with automatic differentiation for complex functions, although the software packages, I believe, do this sort of thing. So yeah, good question. I don't know.
Thank you.